Okay, so today we are talking about some odd and even functions, some asymptotes, and some end behaviors of functions. So the first thing we're looking at is odd and even functions. Sometimes you'll hear it referred to as symmetry. So we can look at this a whole bunch of different ways. We can look at it graphically, numerically, meaning looking at tables, and then algebraically. So we will want to be able to definitely do this algebraically, but support it graphically and numerically. So our first example is talking about symmetry with respect to the y-axis. And this will be referred to as an even function. So if it's an even function, again, graphically I see it's symmetric to the y-axis. If I look at the table to prove numerically, I can see that pattern, that symmetry pattern. And then algebraically, what we want to show is that if I have the function f of x, this will be equal to f of negative x. So in other words, I plug in a negative x, I simplify the function, and it's equal to the original function. So if we try this one, this is saying anywhere I see an x in that function x squared, I plug it in and I make it negative. Now we want to simplify. So if I simplify, take negative x times negative x, that's going to give me a positive x squared. This turns out to be that original function. So what I've just shown algebraically is my original function is equal to the function when x is negated. Our next symmetry is symmetry with respect to the origin, and in other words, we're going to call this an odd function. So I try to make that connection with origin, odd, connect the two O's. If we're looking at an odd function, symmetry, I can think, if we go back to our days of geometry, it's the same thing as a rotation of 180 degrees. So if you can take your function and flip it completely upside down, graphically speaking, you have an odd function. It's got to look the same right side up and upside down. Numerically speaking, if you take a look, when I plug in a positive number, I get out an answer. When I plug in that same number but I negate it, I get out the same answer but negative. Okay, so take a look. I plug in a positive 2, I get out a positive 8. Now I plug in that positive 2, except for this time I make it negative. And what do? I get out a negative 8. So algebraically, what is that going to look like? So that's going to say, okay, I have a negative x value. That should be the same thing as if I negate the whole function. Okay, so what do we have to do here? Well, I have to test both of these situations. So I'm going to say let's test this one first, meaning anywhere in my function I see an x value, I'm going to plug in a negative x, and then I'm going to simplify. So a negative x cubed, well, when we simplify this down, we'll now say negative x cubed. Okay? So this is what happens when we have f of negative x. Notice this is not equal to the original function, so therefore it's not an even function. So we're going to continue, and now we're going to do the second half of the test, which says, okay, take that function, and I want you to think of it as distributing a negative. So if we distribute that negative through and simplify, notice we get negative x cubed. So this is equal to negative f of x. And notice what we get. These two quantities are now equal to each other. So we have just shown algebraically, if I plug in a negative x and simplify, it's the same thing as if I distribute a negative x to the entire function. Okay. Next topic we're going to take a look at is asymptotes. So when we're talking asymptotes, we get both vertical and horizontal asymptotes. So below we have a function, and it's saying it appears to flatten out as we get to the left and to the right. So if I take a look at this function, I can see it's starting to flatten out as I get to the left and as I get to the right. And that is looking like a horizontal line. There's your horizontal asymptote. So on this graph, I can see I have a horizontal asymptote at -2. But we also can have vertical asymptotes. Okay, and if I take a look at the graph again, now up at the top part of the graph, it looks like it's starting to flatten out and get super duper close, not touching, somewhere around -2. Same thing over here, but at +2. So if I'm looking, I can have functions with both vertical and horizontal asymptotes. You're going to notice, hopefully, your vertical asymptotes are going to be the same as that domain restriction. If we were to solve and try and figure out what that domain would be, well, I can't equal 0. So if we solve this, add x squared to each side, and then simplify, notice that would be your domain restriction. That would say it can't equal plus and minus 2, but notice that that's also going to pose your vertical asymptotes. Your horizontal asymptotes are going to be a little bit different. Horizontal asymptotes are going to have a few rules that will go with this. We will have, and if you take a look at this function, take a look at the exponents. Your largest exponent. So my largest exponent in my numerator is a 2. The largest exponent in the denominator is a 2. Okay, so if your exponents are the same, we're going to make the ratio of the coefficients. Okay, so for instance, I'm going to say over here I have some function where I have, we'll call it m to the a divided by n to the b. Okay? And if a is equal to b, if those exponents are equal, then that horizontal asymptote is equal to the ratio of the coefficients. So in this case, I can say your horizontal asymptote is equal to -2. And we'll get into the why behind that in class a little bit more. The one below we're going to take a look at and notice that, well, the ratio of the coefficients, that's not going to work because I'm noticing my largest exponent up here is a 1 and my largest exponent over here is a 2. So that's not going to work. So again, if I'm thinking of function, right, we're going to say, again, n to the a over n to the b, but I notice that numerator exponent is less than the denominator. Okay, so what's going to happen, well, is something different. So let's go and graph this one out. And we can see on that one, so we have a horizontal asymptote that looks like at y equals 0. Okay? So what we want to connect is when we have that situation where the numerator's largest exponent is less than the denominator, the horizontal asymptote is always going to equal y equals 0. And again, we're going to get into the why behind that more in class, but just for the basics right now, just looking for rules, your horizontal asymptote will always be y equals 0 in that case, numerator being less than denominator. To find your vertical asymptotes, just like we said from up above, well, your vertical asymptotes are going to be like trying to find your domain. So I would say, well, if I'm trying to find my domain, I'd want to set that for domain purposes not equal to 0. For asymptote purposes, I'm trying to find that equation, so I will set that equal to 0. And then in order to solve, well, we have to factor. So I want to find something that's going to multiply to be negative 2, add to be negative 1. So I'm going to have a negative 2 and a positive 1. And then we take each of these and set them equal to 0 and solve. So I see one asymptote is going to be at x equaling positive 2. And I see one asymptote is going to be at x equals negative 1. And if we go back and we look at our graph, we can see here's a negative 1, here's a positive 2, and that would support our work algebraically. And the last thing we have to talk about is end behavior. End behavior is connected to, well, the ends of the graph. What's happening as I approach the left-hand side or as I approach the right-hand side. And what we're going to start to connect with this is the concept of limits. So anytime we're talking about end behavior, we're going to use this limit notation. So we always start off with this abbreviation limit, and what we're saying here is as x goes to, well, we want to go to the ends of the graph. So one end is at negative infinity. And I want to read my function and say, well, what's going to happen as that graph goes towards negative infinity? Well, as I'm reading the x, again, I'm going to report what's going on with the y. Well, the y is going up all the way up to the sky. It's never reaching a number. It's never going to stop. So the end behavior of that function is negative infinity. I'm sorry, positive infinity. It's going up and up and up. But if I take a look, now we have two ends of the graph. We have one as it goes to negative infinity, and one as it goes to positive infinity. All right, well, as it goes to positive infinity, again, read the x, report the y. Again, that y value is going up, up, up without end. It goes to positive infinity. So every time we think end behavior, I want to think what's going on at the ends of the graph. So if we look at the second picture here, I want to say, okay, as x goes to negative infinity, what is happening with the function? So as x goes to negative infinity, I see my graph is going to negative infinity, not approaching a number. The only time you will have a limit is if you have a solid number. So not only do we go to negative infinity, but we also go to positive infinity. So as x goes to positive infinity, I'm reading my x values, but reporting out the y values, I can see it's going to positive infinity. It's not hitting a value, so I can't write the value down. Okay, now these are going to be a little different. Same concept. Still saying I have two ends of the graph. As x goes to negative infinity, I want to figure out, well, what's my y value doing? So as x goes to negative infinity, it looks like my y value is starting to approach an asymptote. It's starting to level off. It's getting super duper close to 3. So since it's approaching a number, I can tell you the limit is 3. And now the same thing as I get to the positive side. As x approaches positive infinity, again, read the x, report the y. Again, I can see that function's trying to get to 3. Now, hopefully, we're making that connection with asymptotes and seeing that, well, if I look at the exponents, numerator exponent, denominator exponent, they are equal. And we said above, if they are equal, well, I take the ratio of the coefficients. So the horizontal asymptote on this would be 3 over 1 or 3. And notice that not only is the limit 3, but the horizontal asymptote is 3. Those should check. Okay. Same thing on this last one. So now if I'm taking a look at this function, same idea. I see it's actually approaching a horizontal asymptote. So as I'm going to negative infinity, I'm going to a left-hand side, it looks like my function is trying to get to 0. It's getting super duper close to that x-axis, not going to touch. Same idea if I go to positive infinity. As x goes to positive infinity, I can see again, it looks like the y values are getting so super close to that x-axis, but not going to touch, so equaling 0. And again, if we go back to the horizontal asymptote concept, we know our numerator, the exponent, is less than the denominator's exponent. And when that happens, we are going to notice a horizontal asymptote of y equals 0. And again, end behavior should be checking out with your horizontal asymptotes. Hope you liked the video. Please remember, like and subscribe. Have a great day.